but okay. Welcome to the lecture in progress. We've just remembered to hit record. Okay. Yeah, I'm not going to review this. You can certainly, if you're watching this online, pause it and review this and make sure it makes sense. It should make sense. Um, we showed this result previously. I will add that. Um, yeah, good one, Colton. I was even going to tell people at the beginning to remind me. We showed this previously and we just did it now as a warm-up with the MGF. And and so it's all right here. You should be able to follow this based on last lecture. There was nothing really new here. It was just another example. Okay, let's continue forward then. And yeah, don't hesitate to speak up. If I'm not responding, I may be looking down or looking at my notes or something like that. So I will wrap this up at 3:50, no matter what. All right. So moving forward then with our next topic here, similar topic is a joint MGF. So we make this definition. If X1 to Xn are jointly defined, they could be independent. So in a sense, not have you don't need to have a separate joint distribution. You know, it's the product of the marginals, but in general, they're jointly defined, discrete or continuous, even possible mixtures of those, which we haven't talked about. Then the MGF, the joint MGF, it's called, is given by same thing. You just write the things down here, or you can write it as a vector. Since we won't be doing this much longer, I'm going to not go with the vector notation. Although next semester probably will use that for a lot of things. Okay, so it's just this T1, X1, actually X1, T1 plus dot, 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 plus Xn, Tn. So if you were writing it with a vector, you could write it X transpose T, for example, or the dot product, right? Okay, yeah. So this is called the joint moment generating function. The joint MGF is this for obviously for the random variables X1 to Xn. Okay. Again, it's going to be something here where we can't prove this next theorem and you just have to accept it on its face. Oh my God. I can't remember how to add another page here. All right, well, no big deal really, right? We can just get rid of this stuff. All right. Okay. All right. So the theorem is the same. We'll just go quickly though with this definition. I'm not going to write it out rigorously like I did for the single variable, but we'll just say the joint MGF uniquely determines the joint distribution. Okay. In other words, it would be something like if there is a set in um, Rn where the moment generating function of one vector is equal to that of the other open set, then the distributions are the same. And you just to spell it out. But since we're not going to worry about that too much, and on the theoretical level, as far as doing a proof goes, I think you can just get this from this simple fact. If I can show two joint distributions are the same, then that set of random variables has the same distribution as the other set of random variables. Okay, corollary to this, we're using everything from now on. I mean, there's nothing, I'm just trying to give you more stuff. It's all building towards something. So corollary to this is that if x1, xn are independent, if and only if the joint MGF separates. So this symbol means if and only if, or you can write the words M x1 xn t1 tn is equal to mx1 t1 dot 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 mxn tn. Okay, the proof's really cute in a way, very not hard. Suppose x1, xn are independent or is independent. Okay, then m x1 xn t1 tn must be equal to m x1 t1 m xn tn. Why? Maybe I should show it more slowly in a step. I think I am jumping the gun a little and just writing that down. So let me write the step out a little bit. So we can just for this case just show it in the continuous case maybe. So actually don't need that. I'll just say is equal to E of E to the T1 x1 plus dot 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 plus Tn xn, which is equal to E, write it as a product now, T1 x1 dot 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 E Tn xn. But now this is equal to this product here, because if it's an integral, these separate out. So at this stage, I have a n integral, right? N integrals. I have dx1 to dxn, and this is embedded inside the integral with the joint distribution, this is. But I can separate out them one at a time and associate each with its integral. The other variables or functions of variables are constants with respect to the other integrals. So they all come outside and you just get this. Which is just now equal to that product. So x1, this should be a 1. The writing is degrading a bit. I'll try to keep my game going here. Yes. Okay. Now the other one is maybe the interesting one that you might not have thought of is that if it can separate them like this, they are independent. And why do you think that is? Oh, does anybody have a question? No. Okay, good. So why do you think the other case works? So this is if they're independent. This is this case, right? This is the right arrow. So to show the other one, on the other hand, right? So also, on the other hand, I'll wait. I mean, I'm gonna wait. If anybody has, it's gonna take me about 20 seconds to write the next sentence. If anybody has a reason, you can let me know. On the other hand, if this is true, if mx1 is equal to the product, right, of these, I'll stick to the way I'm doing it here, T1. Then, anyone? Yep. Okay. Yeah, it's okay. So then by uniqueness, that's the key. So by uniqueness, because when x1 to xn are independent, this is true. X1 to xn must be independent. It's true. There are different distributions if you have one set of x1 to xn and another, and their MGFs are not the same. So I mean, if in one case, maybe they're all marginally have the same distribution, but if one case they are independent and in the other case they're not independent, the joint distribution would be different. And so, yes, so if you can do this, you can separate them like this, then because in the independent case that gives you the MGF, that means that because of the uniqueness, the variables have to be independent. Cute. Not, but that's it. That's all you need for that. The real, the pedal hits the metal due to the proof of the uniqueness theorem, which, as I said, is more and much more advanced and complicated and stuff like that. Although doable, um, in the end, it turned out doable. Uh, okay. I like to do a good example now just to show some more of this, and I'll probably have to go up here and erase this stuff. Might be a good time now to just get rid of this. I leave this for you for now. Okay, let's keep going. All right. So as an example of this, should we change color? That will maybe make it clear that. Okay, so say X, Y are IID, normal, mu, sigma squared. Uh, then X plus Y and X minus Y are independent. Should maybe make sense. Obviously, it's not obvious, um, but if you think about it a little, knowing the sum doesn't really tell you how close the two random variables are, nor does how close they are tell you how large or small they are. So I think it's reasonable, but to prove it, um, different matter. Um, so let's do it using the MGF. So we'll say M x plus y. Our first variable, x minus y, is our second variable, t1, t2. It should just roll off the sleeve. But who knows? Let's see how it goes. So this is just equal to, it should be straightforward. So E, just put everything in, x plus y, t1, plus x minus y, t2. Okay, yep, looks okay, looks okay. I have to pop up to the top now. What I'll do now is arrange them by the variable and collect them that way at the top. Okay, I'm going to collect the x one, so what would it be? E to the x t1 plus t2? Yeah, and then plus e to the y t1 minus t2, something like that. Okay, so coming up here, I have equals plus y t1 minus t2. Yep, and now what do I do? Independence of x and y, so these integrals separate out and I can just say x and y are independent. It doesn't matter, I have a t1, t2, I could have a million things up there. As long as I can separate this, I can write these as separate expectations. So this is ex t1 plus t2 times e, right? Because first I'm multiplying using the property of the exponential, and then I'm taking it out. T1 minus T2. Yes, 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 yes. Okay, these I know because x and y are just normal mu sigma squared, so I should be able to write down what these are. So this is equal to, the first one is e to the sigma squared. Yeah, I was writing mu squared first. We'll keep doing that. So, I mean, sorry, mu. So this is E mu T1 plus T2 plus sigma squared T1 plus T2 squared over 2 times E mu T1 minus T2 plus sigma squared T1 minus T2 squared over 2. Okay, now collect the terms so that the mu's are together and the sigma squareds together. You notice the mu has a nice cancellation, so I have E mu T1, 2T1, right? Yeah, 2 mu T, E mu 2T1, so let's write it like real people. And and then I have times the other thing, right, would be, or just combine it in the exponent now. So the sigma squared piece here, I'm going to have this and this. What's going to happen, the cross term, the minus 2t1, t2 will cancel with the plus 2t1, t2, and I'll end up adding the other twos to drop the 2 in the denominator there. So I should get plus sigma squared, I think, sigma squared t1 squared plus t2 squared. That should be it, right? Yep. Okay, one final collection is I want to bring the T1 together and the T2 together so that I can see separate random variables the way it looks now. I have a joint MGF and I can't see what's going on. I can't see the independence quite so well yet, but if I separate them, I'll see it. So this is just E to the 2 mu T1 plus sigma squared T1 squared times e to the sigma squared T2 squared. Okay, so this is what do we have here? So So what is the first one? It's just a normal MGF. So yeah, I think the way you say it though is a little important here. So I could say that so this is like if X1, yeah, let's just say it like this. This is what? This is the MGF for a normal. What's the mean? 2 mu. What's the variance? Well, usually it's sigma squared over 2. So this is 2 sigma squared over 2. So this is 2 sigma squared. And this one is normal. No mean, the mean is 0, and the variance is 2 sigma squared. You should recognize that this is the marginal distribution for x minus y, and this is the marginal distribution for x plus y. But the real result here is that they separate and that they are independent. So the final thing to say is because this is the joint MGF, you don't have to use the word joint, you could just say MGF for a uh, for a normal 2 mu 2 sigma squared RV and normal 0 2 sigma squared RV that are independent because they're multiplying. That implies x plus y, x minus y are independent. Okay, that's the big result from that one. Okay, well, we expected that. And it was more of an exercise than anything else, just to get used to this. Any questions so far? Okay. Is anybody here? Yeah, okay, everybody's still here. Yeah, thanks. Cool. Um, you do wonder sometimes you look away for a while, it's pretty quiet, but that's good. We're getting through it. Thank you, people. Yep. Gotcha. Okay, let's keep going. A little more. We're getting to something pretty exciting. Okay. Yep. Okay, so multivariate normal. We're going to define it again. And I don't know if you remember, but when I did define it, I said there were different ways to define it. And we're doing it in a way today that is easily identifiable with the way we did it last time and even more general, just to make the result of the proof more general. Um, okay. Okay, so I'll just define it again. This is good review anyway. So multivariate normal. Again, for you people continuing, I don't mean to estrange the people that aren't continuing in the course, but just for the takes 10 seconds to say this, but and maybe to, if you are continuing, you can kind of think of Math 218 starting now a little bit, but it's not necessarily going to stay in this direction, but this is stuff we're going to use. So Okay, so multivariate normal, say the definition goes as follows, so is defined by the following. So say we have Z1, so the same idea as before, Zn, IID, normal, 0, 1. So if either one, right? And then I say x1 is equal to, and I can just write this without worrying about the variance and the mean. I could just put constants here and just say it's a linear function of these, right? That's what I'm telling you. Not that you should necessarily know this. I'll just say like this. And of course, this lends itself really well to matrices, but we're not going to go there because short amount of time left. And say I have xm, m and n don't need to be equal. Usually there's some waste going on if they're not equal, but some results, sometimes the situation you have, they're not equal. So a m, no, yeah, column one, yeah, a m1 z1 plus a mn zn plus mu m. So I have m rows, n columns. Let's see. Can m can definitely be less than n. Um, I think it could be greater than two, but it would be a case I'm not as used to. So let's just leave this alone for now and just say in general it can be defined this way. It certainly can be. Okay, so the AIJs, the important thing is AIJs and the mu j's or the mu i's are constants. And then you have a definition of then we say x1, and you can put this in vector notation if you want, to xm is our m variate, or just say multivariate. M stands for the little variable m, the m variate normal. Okay, and then the system defines it. And you could compute from this system, right? You could compute the means. Well, the means are visible, but you could compute the covariances and the variances easily from the system using the independence, right, of the z's and yeah, and the basic rules of independence. So you get practice with problem 1 in the homework 8. Okay, note, just point this out marginally. Okay, so that's the definition. So here's the definition right here, using that above, right? So marginally, let's just examine it a little. Marginally, we know the distribution of each x. I say xi is normal, mu I, and what's the variance would be the sum of the ith row squared, right? So it would be ai j squared from j going from 1 to n over the columns here. Okay, but they're not, probably not, or not unless it's diagonal or something, they're not going to be independent, and they have a joint distribution. The joint distribution is completely already specified by this system, but and you can derive a joint PDF as well. Might take you a few months or something, but you could do it. Depends how big M is. But we can also use the joint MGF. So the joint MGF is as follows. Let me come up to the top, and the joint MGF will be, use the object eraser. Okay, so the joint MGF is just going to be the following. Yeah, let's try to get away and write. Change the color maybe. Okay, so the joint MGF is MX1 XM T1 TM, and this is just equal to, yeah, I got to multiply each xi times the ti, right? So this is equal to e to the sum 1 to m. So across the rows, ti xi, or we usually write xi ti and think of this as a function of the ti's. Okay, correct? So I'm teaching each of those xi's, multiplying by ti's. Each of the xi's are in turn sums of independent normals and constants. So let's write this big mess down. What is the distribution of that exponent? So we will write this here where the sum 1 to m xi ti is, okay, is it normal? It should be normal, right? Because everything's normal. The xi's are marginally normal, and we know that if we add normals, we get another normal. Now, they're not independent, but if I were to think about the way I'm adding them, and I'm adding the same things, I would be adding the same z1s. So in the end, the sum would also be a function of the z1s, just with different coefficients than the individual xi's. It would be the sum of all those things, and then, but it would still be normal because it would be, you could write it as a sum of just z1 through zn plus a constant. Yes, it's true. So this is normal. The mean is just the sum of the means. All the zi's have means of zeros, so those you don't need to worry about. So it's the sum 1 to m ti mu I. And what is the variance of this guy? Where's my, so this one here, what is the variance of this? It's the variance of the sum of things. It's the same thing. So the best way to take a variance of a sum is to take the covariance of the thing with itself and then apply the property that covariance of sums are the sums of the covariances pairwise. So the variance of this is the covariance of it with itself, and then I can apply that property. Okay, so yes, so this is, let's go back to this. This is the covariance of this with itself. I wonder if I should do this in two steps, maybe. Covariance of the sum 1 to m xi ti and the sum, let's use a different letter xj or xk tk. Yeah, I could have used j. Okay. Okay, that's the way to do that. And then I can use or I can use the property of covariance here. Don't give up. We're almost to the miracle. So mu I. Okay, this is just the double sum, right, of the covariances. I can also pull out the Ti and the Tk here. So 1 to m, 1 to m, Ti, Tk, covariance xi, xk. Ah, look at that. Look at that. Okay, yep. All right, so this is it, actually. Might not have noticed that something happened. I don't blame you. First time, it's a lot of stuff going on at once, but you can see since the MGF completely specifies the distribution, we've reduced it to just a few things that the distribution depends on. You can read the notes too for more verbose or written out explanation of this, but I think it helps to hear it too. And yeah, so what am I saying here? As long as, right, as long as, so if I take a multivariate normal, let's summarize. So if I take a multivariate normal, I always get this for the MGF here. Let's go. Okay, what is this? Well, we worked at it a little. We said this is a normal distribution. Its normal is TIs, which is just part of the MGF times the mu i's of the variables. And then also I need to know the variance of this so that I can do it, right? This is the key to, or yeah, this is the key to the MGF. So so if I know, in other words, if I know this distribution, I know the MGF, right? Because I'm just taking the expected value of an exponential of a random variable. Complicated random variable, but a random variable nevertheless. And I know the distribution, so I should be able to do it. I can think of the t's as being part of this distribution for now. They're just going to survive the expected value. That's fine. Okay, so this is the thing I need to focus on. Now look at the what it is. It's normal for sure. Its mean is this for sure. What do I need to know the mean? The TIs are given. All I need to know are the M mu i's, right? Okay, what about the variance of the normal? Okay, the TIs are given. All I need to know um, are the M squared covariances. It's not actually really M squared, right? This is actually, uh, it's M choose 2 for the off diagonal ones when they're not equal plus M for the variances, right? So this is how many of these are. This is M. So just like before, it's all the covariances for, and then all the variances and all the expected values, all the means. If you know that, you know the distribution. It's what I told you in class, but I didn't show it to you. And you might argue I still didn't show it to you because I didn't prove the uniqueness of it. But if you accept the uniqueness, then this is a good backup for that. And now you should feel comfortable, at least more comfortable, resetting your multivariate normal using any constants you want in the linear system, as long as you attain the correct set of parameters of size 2m plus m choose 2. Okay, this is going to allow us to do this next proof, which is extremely this next theorem, to state this theorem and prove the theorem and do one example with it. So that's all that's left in the class. We have 10 minutes. I want to write the theorem down at least and show you one way it can be used. And then we'll finish the proof of it next time using this uniqueness of the joint MGF for the, yeah, for in the general case. So let's continue on for now. I said I would wrap it up at 3:50. I was not lying. If you need to go, feel free and go. I can't control you. I'm far away from you. So, okay. So, what do we have? Here's our big theorem now, and we're going to do a proof for this too. So, theorem. Okay, say x1 to xn, back to n now, are IID normal mu sigma squared. Then, period. Then, three things. One we showed earlier in the class. That's fine. X bar is normal. Mu, we did this a month ago, right? Sigma squared over n. Okay. The other thing is we can take n minus 1 times s squared and divide it by sigma squared. I'll tell you what s squared is just in case that is not part of your vocabulary now. I don't remember. Is chi square with n minus 1 degrees of freedom. So the parameter is n minus 1. And x bar and s squared are independent. Three things. One we approved already. I'll remind you what s squared is. S squared is this called the sample variance. We did do a problem in it, but in case this escaped you, this is 1 over n minus 1, sum 1 to n, xi minus x bar squared. It's called sample variance, and you notice there are no parameters in it. It's just something you can compute from data. Okay, no parameters, no sigma squared, no mu in it, just like x bar is it's a statistic, comes exclusively entirely from a sample. All right, give me a moment here. We'll finish the proof next time, but I want to wrap this up a little bit with a nice application of it, and then we're done. And when we do the proof next time, and by the way, feel free to maximize it. Feel free to try to read it and understand first. Ross does a similar proof in the book in 7.8. And there are lots of them, but a lot of them are different types. They use different ways to do it. This is one of the easier ways to do it because it uses this heavy duty theorem. But it's interesting. But if you don't want to do it too, that's okay. We'll get. It's not so much about this proof, but it's more practice with the MGF. Okay, and also believing this fact. It's very useful. Okay, and this is what I want to show you now, and then I'm done. 7 minutes to go. So, okay, so yeah. So the thing is, yeah, like we can make a really nice confidence interval now for mu, the mean of a sample, given that we only are assuming that the sample is IID and normal. I'm not making any assumption about mu and sigma squared. I can create the confidence interval based on only the sample, which is valuable. Now let's recall. So here's a good application of it. So recall, and then the proof will follow next time. So recall, we said the definition of a t random variable, if I say t is equal to z over the square root of, say, y over nu, Greek letter nu, at where z is normal 0, 1, and y is chi square nu are independent, then T is said to have a T distribution with nu degrees of freedom. Okay, and the density for that, which remember we did the long proof, we said f of t was equal to nu plus t squared to the minus, sorry, yep, no, that's right, nu plus t squared to the minus nu plus 1 over 2 power. So another better way to write it, maybe see it better, is 1 over nu plus t squared to the nu plus 1 over 2. So you can see the symmetry, right? And it turns out this does look and asymptotically approaches a normal too. So it's similar to a normal, but different. Yes, so now I can build something with a t distribution out of my sample up here. So this is just an application, this part. It's not part of the theorem anymore. I just want to finish this and then I'm done. I'm seeing the end of it. Okay, so then I have, what do we have? We have from our sample, returning to this theorem, X bar minus mu, right? That's its mean over sigma squared over n. So sigma squared over n, square root, right? Which I can write X bar minus mu over sigma square root of n is normal 0, 1. Also, what if we take n minus 1 times s squared over sigma squared? Well, this is, and if I divide this by, so assuming this is chi squared n minus 1, if I divide this by n minus 1, I will get y divided by nu, right? So if I divide this by n minus 1, we get s squared over sigma squared, which has the same distribution, which is a chi-square n minus 1 divided by n minus 1, RV. Okay, so now let's build T since s squared and x bar are independent. That's the key. That's usually hard to prove and keeps teachers from doing this thing. Then we say that we can take the quotient here, right? I'm going to take x bar minus mu over sigma square root of n and divide by the square root of, what is it, s squared, this thing divided by n minus 1, or this s squared over sigma squared is equal to x bar minus mu over s times the square root of n. So s has replaced sigma, and it looks like, oh, I'm just replacing the sample standard deviation, the actual standard deviation with the sample standard deviation. Yeah, that's what's happening. But we just showed, if you believe the theorem, that this has a t distribution. So this is t with how many degrees of freedom? N minus 1, right? N minus 1. That's what I divided by here. Just like in here, I divided by nu. So this is has a t distribution with n minus 1 degrees of freedom. We have functions in R that can calculate quantiles, qt, and pt that can calculate quantiles based on this distribution. So let me just write down one thing. Like if I want as a final thing, if I want, say, hold on. We'll go to green for this last thing here. So if I want to say a 95% confidence interval for mu, notice you don't need to make any other assumptions, just normality and IID. And then you can do this, and then you could use R. So you could do this, say, over Thanksgiving. You could say, I don't know, you could ask your guests, I don't know, like their age or something, and then in months or something or whatever in years. And then, yeah, and then you could find a confidence interval for the mean of your guest's height, something like that. Okay, so what would the confidence interval be? So I could now make the statement, the last statement, I could say something like the probability that, under the assumption that it's normal, x bar minus mu over s, all calculatable from the sample, is less than QT. So that's the quantile. I'm going to make a 95% one, 0.975, n minus 1. If you have 15 guests, you would use 14 here. And you would say this is equal to, now because you're taking the absolute value here, you're excluding zero point 0.5, a probability of 0.05. Okay, so there's still a 0.05 probability that this is not the case. So this is equal to 0.95. This is called a 95% confidence interval. In other words, the 95% confidence limits are this. So confidence limits, in other words, we generally, if we do this, we are expecting that the center is the estimator and the confidence limits are given, but we really write it like this. So this is our expected best guess at the mean. And then I can write the rest by multiplying through here, and I get S over the square root of n times qt, n minus 1. No, n. Yep. Right? It was n. Yep. qt 0.975. Here's where the n minus 1 goes. Yep. For mu. Take the average, calculate the sample variance, take the square root of that, divide by the square root of n. Go to R, calculate this. You can get your confidence interval for that. Okay, it's 3:52. I'm going to stop recording, but I'll stay online. And I've got time. So if anybody wants to talk, you can stay on. If you don't want to talk, you can stay on or you can leave. Let me stop recording. Okay.